Okay. So today I want to talk about a number of things related to spectrum. The first thing I want to talk about is what we call interlacing. And each way to remember this is if we have a graph X and we have a vertex A, then the statement we want is between any two eigenvalues of X, there's an eigenvalue of A. Now, this doesn't refer to multiplicity. So if X is the graph length vertices, we assume there are n eigenvalues, θ1 through θn, in decreasing order, say. And so if X has an eigenvalue of multiplicity 3, then you've got 3 copies of theta. And so between those 3 copies, there must be 2 eigenvalues of X drop A. So one consequence of interlacing is that when you delete a vertex, the multiplicity of the eigenvalue is changed by most 1. They can go down by 1, stay constant, or go up by 1. So it's giving you general information about the spectrum. Now, there's more than one way of proving this, and I'm going to prove it using some of the theory we have about generating functions and the like. So here it is. So we're assuming I've got a graph on n vertices, and the eigenvalues are given in this form. Now, normally when I write down the eigenvalues, I tend to assume that I'm dealing with the distinct eigenvalues, but today we're not, or now we're not. And so the theorem is if X is a graph on n vertices, Y is an inducible graph on m vertices, then the ith largest eigenvalue of Y is less than or equal to the ith largest eigenvalue of X, and the m minus ith eigenvalue of Y is greater than or equal to the n minus ith eigenvalue of X. So one consequence of this is that the largest eigenvalue of Y is less than or equal to the largest eigenvalue of X, and the smallest eigenvalue of Y is greater than or equal to the smallest eigenvalue of X. Now, there's another way of seeing that, which I'll show you shortly. But so the eigenvalues of the induced subgraph lie between the eigenvalues of the graph. And since I'm going to give a proof by picture, I want to work with the rational function 5x drop A over 5x. That I'm leaving out the t there, but let's not worry about that. And the result follows from the assertion that if you plot the graph of this function, that the derivative is negative everywhere it's defined. Now, the problem is if you're looking at it, if there's an eigenvalue theta of x, which is not an eigenvalue of x drop A, then that rational function has a pole at A. Okay, and so the function is not defined. But so aside from that, any point where the function is defined, the derivative is negative. And from that, we'll get the interlacing formula. Now, to prove that statement about derivative, it's actually fairly simple. The real point is the derivative of 1 over x minus theta. The derivative of this is negative everywhere it's defined. And that's an exercise in your first calculus course. Now, we have that our rational function has got this expansion in terms of the spectrum coming from the spectral decomposition. So we have a sum. So we have a linear combination of things that are form 1 over t minus theta r. Okay, now what about the coefficients here? Well, E sub r is positive semi-definite, and so its diagonal entries are non-negative. Now, you should be able to supply at least 2 proofs of that, but the simplest one to say is, well, the principal submatrices are positive indefinite matrix are positive semi-definite, and this is a 1-by-1 principal submatrix. So the coefficients here are all non-negative, and then since each term has got negative derivative everywhere except at theta r, we get the claim they make. Okay, and I've actually done the calculus for you here just to show off. Okay, now the best way to see the proof is to think about the graph. Now, theta x, 5x is a polynomial of degree n monic, and this is a monic polynomial of degree n minus 1. So for large x, it's going to look like the graph of 1 on x. Okay, and so we expect to see it asymptotic from below to the x-axis on the left and from above on the right. Let's put an arrow on this just for the fun of it. So then the other places Well, as I said, it must look like this. The derivative is negative, okay? And you think about it, at a pole, it's going to be coming down essentially vertically and then gradually move away and then go like this next pole. So between each two poles, the graph looks like just like this. And so we get a picture like this. There's some more stuff in the middle. And so the poles are at the zeros of theta 1, theta 2. That's a slight lie because there can be some cancellation. If an eigenvalue's got the same opacity for x next drop a, it disappears and we can ignore it. Okay, so we can, but I haven't fussed with that here. And so the point is that between each two poles, there has to be the curve has to go through zero, and so that gives you an eigenvalue of x drop a. Now, this is useful if you can prove things like interlacing is more general just for characteristic polymers, but actually it's subgraphs. Let me go back. Where is it? So you could say a polymer of degree n minus 1 will interlace polymers of degree n if they've both got real roots, and between each two zeros of Pn, there's a zero of Pn minus 1. So you have interlacing that form. One thing this result tells you that interlacing is equivalent to these guys being non-negative. And so if Q1 and Q2 interlace P, then so does their sum. Okay, now so I'm just pointing out there are other things you can deduce from this, but all we're saying is because these coefficients here are non-negative, we get the interlacing. It follows from that. And so now the other proof of this involves, well, actually, let's not worry about it. I claimed that the largest eigenvalue of x drop a was less than or equal to the largest eigenvalue of x, and that the smallest eigenvalue of x drop a was greater than or equal to blah, blah. So I want to sketch a proof of this. So suppose I've got a graph x, and I'm using rho for the largest eigenvalue and tau for the smallest eigenvalue. Then the matrix rho I minus a is a symmetric matrix, and all its eigenvalues are non-negative, so it's positively definite. And since principal submatrices are positively definite, matrices are positively definite, we see that if y is an induced subgraph of x, then theta max of y is less than or equal to rho. And for the other second result, you look at a minus tau I. That's again positively definite, all its eigenvalues non-negative, and you deduce this. Okay. The Perrin-Frobenius theorem tells you that if x is connected, then this inclusion here is strict, but I don't think we'll need that for the time being, so I won't worry about that. So the point is that the positive semi-definiteness will give you part of the interlacing, and in a certain sense, if you work away, you can get the complete interlacing from that too, but one proof's enough for now. Any questions at this point? So this gives us a feeling for the spectrum and for the relation between the spectrum of the graph and the spectrum of the vertically subgraph. Now, the topic I want to be talking about most today is questions about cospectral graphs. Now, as far as the quantum walks are concerned, we're not going to worry too much about cospectral graphs, but some of the machinery we build up will be very useful. So the two graphs are cospectral if their adjacency matrices are similar. And to give an automatic, as written here, to give a completely trivial example, isomorphic graphs are cospectral because if they're isomorphic, you get from one adjacent, you get the adjacency matrix B from adjacency matrix A by writing it as P, A, P transpose, or P is a permutation matrix, and permutation matrices are orthogonal, and so the adjacency matrices are similar. So that's isomorphic graphs are cospectral. It's worth noting, just to worry you, that if two graphs are isomorphic, it does not follow that their adjacency matrices are equal. If you write down the adjacency matrix for these two graphs, those matrices will not be equal. This is worth remembering once in a while because most of the parameters that you talk about in graph theory are just parameters that are just determined by the isomorphism class. So connectivity, eigenvalues, all these things just depend on the isolation class. But occasionally you need to remember that the adjacency matrix itself determines the graph. Okay, and so you can write down the matrices. I mean, so we'd have one's adjacent to two. This is the obvious ordering. And this guy's going to have 0, 0, 1's adjacent to 3. And 3 is adjacent to 2. So there are the two adjacent matrices. They're not equal. Now you can permute one to the other, and that's what we care about. Okay. Now another minor point here is you're dealing with directed graphs. Well, it is no longer true that two asymmetric matrices are similar if their characteristic polynomials are equal. Okay, so so the example would be 0, 0, 1. So I'm writing down adjacency matrices. Both the characteristic matrix polynomial of both these matrices is T cubed. But these two matrices are not similar. I mean, this has got rank 1, this has got rank 2. Okay, so if you're dealing with directed graphs, you got to be a little careful. I think people, and so the point is, I think that similarity is the right condition. But we won't be dealing with directed graphs, not very much anyway. Now, the thing, once you see, you define the spectrum of graph and you realize it's an invariant of the isomorphism class. If two graphs are isomorphic, they have the same spectrum. The spectrum is just the, the eigenvalues are graphed together with multiplicities. I don't like multi-sets much, but the multi-set of eigenvalues. So if two graphs have the same eigenvalues, so that means the same eigenvalues, the same multiplicities, then the characteristic polynomials are equal, and so the co-spectral matrices are similar. Okay. Now, and once you see that, you think, oh, maybe I can use this to resolve graph isomorphism questions. And I suspect that this question was open for all of about 5 minutes when somebody first thought about it. So you start looking for small graphs. Are there graphs which are co-spectral or non-isomorphic? The smallest ones is this smallest. Oops, that's not what I want to do. The smallest ones are this pair. Okay, so there's two graphs on 5 vertices. Notice that these are essentially complete bipolar graphs. So this is K14 and this is K22 with an isolated vertex. And so if you think about that and you work out the formula for the characteristic polynomial of the complete bipolar graph KMN, you can construct lots of examples. Now, so you say co-spectral graphs are isomorphic, and then someone comes up with this pair, and so the immediate reaction is, oh, I meant connected graphs. Well, that doesn't work either. And here's the smallest pair of connected co-spectral graphs. Now, they're not isomorphic because this one's got 2 vertices degree 1. This has only 1. Okay, so that's fine. 2 more examples. This example here is actually reasonably important. It comes back to something we call local switching. But these 2 graphs are co-spectral. And not only that, their complements are co-spectral. Now, we didn't ask about complements. We didn't care about complements, but the point is we're getting it for free. And what tends to happen, at least with the graphs up to 10 or 11 vertices, is when graphs are co-spectral, the complements tend to be co-spectral as well. So you get that for free. And so it's natural to ask. So you've got 2 relations now. Are they co-spectral? Are they co-spectral with co-spectral complements? And that can happen, and it happens here, and there are many more examples. And here are the 2 smallest trees that are co-spectral on 8 vertices. Now, it's kind of interesting. We have constructions with generalized A, B, and C. I don't know any nice construction which would generalize this. It's pretty common when you're dealing with the spectrum of graphs that if you find a pair of graphs that are co-spectral, it's very often the case you can stare at it for a while and then come up with a generalization and prove more families are co-spectral. And I'll come back to that. So, and these are just found by, These were certainly found by computer search. What's going on? These may well be found, or have been found by hand, although I've forgotten how many graphs there are on 6 vertices. Oh, right, what's going on with that? Oh, dear. Yeah. So some more examples. Now, this is going to lead to a large family of examples. We have graphs called Latin square graphs. Now, Latin square graphs are regular, okay? And here for your amusement is a 4x4 Latin square. It's the addition table for Z4, okay? Now, so you have an n by n Latin square. This in, you have an n by n Latin square. And well, I can define adjacency in 2 ways. But from the Latin square, I get a collection of triples. I get n squared triples. I take the row, the column, and the entry. And I get n squared triples. The entries of the triples are coming from 0 through n. Okay. Now, it's the possible. We can write out the triples in this form. Just write them out as a n squared by 3 matrix. That matrix called an orthogonal array. And it's got the property that if you pick any 2 columns and run down them, you run down any pair of columns, you see each ordered pair of entries exactly once. Okay, so in the first 2 columns, there's a you can see 0, 2 would occur exactly once. I was too lazy to write them all out. There's only 16, but there it is. So the advantage of the orthogonal array description is it corresponds the first column corresponds to the rows, the second column corresponds to the columns, and the third column corresponds to the colors. And so when you look at this, think of this, and you look at a Latin square with you've got rows, columns, and colors, you tend to think of the colors as being essentially different from rows and columns, but they're not. Okay, in this sense, in particular, if I swap the second and third, if I swap the first 2 columns, then I'm taking the transpose of my Latin square. Okay. Now, Latin square's got the property, I should have said this, that you've got n squared entries from 0 through n minus 1, and every entry occurs exactly once in each row, once in each column. Okay. But if I swap the first and second columns here, I take the transpose of the square. But I also see that if I swap the second and third columns, I still have a Latin square. It won't be the transpose. And so somehow you're swapping colors in a column. But you can do that, and it's a natural operation. And there are a number of equivalence relations on Latin. When you say 2 Latin squares is the same, for our purposes, 2 Latin squares are the same. If the graph is the same, what's the graph? The graph has 2 descriptions. One is the vertices are the cells. The cells, so there are n squared cells, 16 cells, and 2 cells are deemed to be adjacent if they're in the same row, or they're in the same column, or they contain the same color. Over here, that means that 2 triples are adjacent if they agree on some entry. They can't agree on 2 entries, because then it wouldn't be a Latin square. So any 2 rows agree on at most 1 entry. Okay. So any questions about this at this point? So the thing about the Latin squares is there are an awful lot of them, and the number grows very quickly. Now, up to sort of the equivalent we're talking about on for 4x4 Latin squares, there are just 2. There are essentially 2, as happened just the multiplication table for the integers mod 4 and the multiplication table for Z2 times Z2. So in particular, the multiplication table of any group is a Latin square. And so that gives you a way of constructing lots of Latin squares, but most Latin squares don't come. There are huge numbers of Latin squares, and most of them don't come from groups. Okay, the numbers don't start to blow up till you get about 7 or 8, but once they do grow up, they're growing very, very fast. There's a huge number of these things. The other thing is, okay, so we're getting a big class of graphs. Now, we can see that I claim a number of things. First thing is I claim that the graph I'm constructing is regular. So if we think about the triples, so this is one of our vertices that corresponds to that square. And now there are three things in the same row, three things in the same column, and three with the same entry. So you get you get a 3n minus 3 regular graph. So, and the one thing which we're not going into, it's been proved that the proportion of Latin square graphs on n squared vertices that have a non-identity automorphism goes to 0 as n goes to infinity. So most of these graphs are asymmetric. Okay, a number of times I've read papers and people have made some claims about things regular and having automorphisms. Latin squares are sort of the first thing to test things on, so that because Latin square graphs are on the whole asymmetric. Now, as I said, you've got to go to reasonable size before that becomes true, but it's, by n equals 10, you're okay. Now, you may say a graph on 10 vertices, n equals 10, that's a graph on 100 vertices. You might think that's not a small graph, but as far as my undergraduate graph theory courses, I'd say, well, small graphs are graphs of less than 10,000 vertices. Graphs are big. Okay, that's why the subject is hard, because you're talking about the small ones are not always, often not typical. Okay, so it's an n squared 3n minus 3 regular graph on n cubed vertices, but it's more as an example of a strongly regular graph. And these will come up once or twice when we're talking about quantum walks, so I thought I would give the definition. So a graph is strongly regular if there are constants Ka and C such that the graph is K regular. Two adjacent vertices, now adjacent vertices necessarily distinct, have exactly A common neighbors. Two distinct non-adjacent vertices have exactly C common neighbors. Now, in all cases, we're concerned about C will be positive, and so the graph will have diameter 2. Two vertices are either adjacent or they're at distance 2 and they've got exactly C, or they're not adjacent, they're not equal. In that case, they've got C common neighbors. And this is a somewhat annoying convention. The convention is that the complete graphs and empty graphs are not considered strongly regular. Now, this is the standard usage by people working in the area. It's not the definition on Wikipedia, for example, but you should be very careful using Wikipedia as a source for definitions. The definitions in Wikipedia are written by the people who fuss most about the terminology and not necessarily by the people that are working with it. I'm not going to penalize you to get confused on this, but the convention, it's a convention that the strongly regular graphs are not complete or empty. So the complete graph is not considered to be strongly regular, and nor is its complement. Okay, so you can go back. I think I'll go back and check. So you can pick any two adjacent vertices. So and see how many common neighbors they come. It's probably a little easier to think about in terms of the orthogonal array. So you pick two of the things and then test how many common neighbors. So you need a triple which agrees with this in one coordinate and this in one coordinate. Okay, and so it could have a 0 in the first coordinate and then some garbage after that. So there are n triples starting with 0, and so you get n minus 2 things adjacent to both. But there's also, you find another 4, I think it is, that are adjacent, that don't have 0 here, but are adjacent to both those. Now you get another 2, sorry. So the answer is n, I believe. I didn't prepare that. I can't leave it for you. And secondly, that you can check the two distinct non-adjacent vertices. So you take two triples with nothing in common. They have exactly 9 common neighbors. you pick something that agrees on the first coordinate, something agrees on the second coordinate, and then you play with the third. So you've got actually 6. So you've got 6. Let's write that down. So for Latin square graph, this is 6. This is n, and this would be 3. Yeah, I finally got there. So Latin square graphs are strongly regular. There are a number of other examples. Well, lots of examples. But these are the easiest. This is the easiest infinite, well, one of the easiest infinite families to construct. So what are some concrete examples? If you take a number of disjoint copies of the complete graph, so you take at least 2 disjoint copies of a complete graph on at least 2 vertices, that's strongly regular, and you can check, and that will have c equals 0. Or you can take the complement. Now, the jargon is that a strongly regular graph is primitive. Sorry about this, you should see me typing. So x and x bar are connected. And if this is going to be a course in algebraic graph theory, we would be working through these things. This is all discussed in my book with Gordon. The point is that the only in primitive strongly regular graphs are these 2 guys, these 2 families. So okay, so in general, if you're doing a strongly regular graph, you can assume that the graph is connected and the complement is connected. If it's not, you're in one of these guys. The Latin square graphs are strongly regular. Now, here's a stranger example. You take the 2 by 2 matrices over a finite field and declare them to be adjacent if their difference has rank 1. That is a strongly regular graph on a large number of vertices. And the fourth one I've got here is the line graphs of Kn and Knn. Now, of course, I haven't defined line graph. So no, we want vertices. The edges. And edges are adjacent to the line graph. If they have exactly one vertex in common. Since this is not a course in strongly regular graphs, we won't have much occasion. I'm just going to say so. The point is that the line graphs is a construction which is sometimes useful, and the line graphs of the complete bipolar graphs give you, complete graphs give you strongly regular graphs, and the line graphs of complete bipolar graphs give you strongly regular graphs if the size of the 2 parts are equal. If they're not equal, then the graph's not regular. So there's an example. So that there are plenty of them. They turn up in lots of places, and for our purposes, Latin square graphs are there. And often when we're thinking about quantum walks, it can be interesting to think about what happens on a strongly regular graph. Okay, you can see what happens on a complete graph without too much trouble. And so, in some sense, this is the next. You could view this as the next class. Now, the point I want to make is I gave a definition of a strongly regular graph in terms of 2 vertices being, you take 2 vertices and the number of common neighbors is K, A, or C, depending on whether they're equal, adjacent, or distinct and non-adjacent. Now, there's a linear algebra definition, which is often more useful. So if we go down in terms of the adjacency matrix, the graph is strongly regular if only if it's adjacency with parameters K, A, and C. And to usually put number of vertices in there too, but the graph is strongly regular with parameters K, A, and C if this condition holds. So that says A squared is a linear combination of I, A, and the adjacency matrix, the complement. this is now this isn't too hard to see. If I take, so I have a K regular graph and I square it, what are the diagonal entries? Well, they're the dot products of the rows with themselves, and each row's got K1s and everything else is 0. So the entries on the diagonal of A squared are all K, the balancing. Okay, so that's where this comes from. Now, the key thing is, in fact, that the ij entry of A squared is counting the number of walks from I to j of length 2. And so if I and j are equal, let's say u and v, if u and v are equal, then there are k walks of length 2 from u to itself, just go out along an edge and come back. If u and v are adjacent, the number of walks of length 2 is the number of common neighbors, and that's A. So you see, so you have exactly this. And if they're not adjacent and they're not equal, then they have exactly C common neighbors, and that's where the C comes from. So this is equivalent to the definition. Okay, and so which you use is your choice. So you probably end up using this a little bit more. Now, it's often convenient to rewrite this expression in this form. So you've got a quadratic polynomial A equal to a constant times J. Now, from this, you can work out the eigenvalues and the multiplicities of the strongly regular graph. And in particular, you can show that there will only be 3 eigenvalues, the valency and 2 more. Did I say that? Yeah, okay, let's work through this. We can actually see this. If X is strongly regular with n vertices, and so 4 parameters, n, k, a, and c, k, a, and c determine n. In fact, only 3 of those parameters determine the 4th, but that's not even an exercise at this point. And take the all once vector. Well, it's an eigenvector with eigenvalue k. And if the graph's connected, it's a simple eigenvalue. And so, okay, so that's one eigenvector with eigenvalue k. If suppose Z is an eigenvector for A with eigenvalue lambda, if lambda is not equal to k, then by linear algebra, the eigenvector Z must be orthogonal to the all once vector. So when I apply the left-hand side, the right-hand side to the all one to Z, or Z orthogonal to the all once vector, this is the outer product of the all once vector with its transpose. So if I apply J to Z, I get 0. And so then I get the relation, well, I've written here that so CJZ is 0, and that's equal to this, but A squared Z is lambda squared Z, and AZ is lambda Z, and this is just K. And so the conclusion is that the lambda is a 0 of this. So what that tells us is that if the graph is correct, if the graph, we're assuming the graph's connected, if the graph's connected, there are 2 further eigenvalues, there are zeros of this quadratic polynomial, until you get 3 eigenvalues. Now, a symmetric matrix with 1 eigenvalue is just a multiple of the identity. The eigenvalues of the complete graph are n minus 1 and minus 1, so it has 2 eigenvalues. And so the challenge is that to prove that if the graph has exactly 2 eigenvalues, it's complete graph. And so sometimes people define strongly regular graphs as regular graphs with 3 eigenvalues. Okay, and that excludes the complete graphs and empty graphs without any more fuss. Okay, and so you get an expression for the eigenvalues, and so I won't have any occasion to worry about that now, so I won't go into it. Any questions at this point? I will be making use of this identity. This tells you that A squared, well, this one actually tells you A squared is a linear combination of I, A, and J. And if you think about it a little bit, it also implies that A cubed is a linear combination of I, A, and J. And so any power of A is a linear combination of I, A, and J. And so the idempotencies of spectral decomposition of polynomials in A, so they're linear combinations of I, A, and J. So there's a lot of information hiding there. I don't need that now, so I won't bother you with it. Now, so I want to pull out some simple consequences of graphs being co-spectral. So I've got, I mean, I haven't even called this a theorem. It's just a lemma. If I've got two graphs X and Y, there's three statements here. They're equivalent. The fact is that X and Y are co-spectral, but their adjacency matrix is similar. Now, if the adjacency matrix A and B is similar, then the trace of A is equal to trace of B, or that's just 0 equals 0. But the trace of A to the K is equal to trace of B to the K for all K. Okay. Now that's now the trace of A to the K is the number of closed walks on a graph of length K. So two graphs co-spectral, then the number of closed walks of length K is the same for both graphs. And the third statement is basically the generating function version of the second statement. This is the generating function for closed walks. We discussed that in the last lecture. And so this is just a disguised form of that. And so this is the real point I'm making, that the number of walks on either side is equal. Now, I'm not going to use this as a permanent notation, but for the purpose of the next few minutes, if CK denotes the number of closed walks for length K, we can say a bit about it. It's worth thinking a little bit. C0 is n, the number of vertices. A vertex by itself is a closed walk of length 0. What I'm really doing here is spelling out some of the boundary cases for closed walks. C1 is 0. There are no, if our graphs have no loops, and so there are no closed walks of length 1. Okay. C2 is the trace of A squared. Now, we saw an example with a K regular graph. A squared's got diagonal entries all equal to K, and so the trace of A squared is n times K, which is twice the number of edges. Now, that's true whether the graph is regular or not, because the diagonal entry of A squared is just the valency of the rth diagonal entry of A squared is the valency of the rth vertex. Okay, and the sum of the valencies is twice the number of edges. Okay, so we get C2 is twice the number of edges. If you think about it for a while, it's not too hard to see that the C3 is going to be 6 times the number of triangles. Okay, so and so if the graph has no triangles, then C3 will be 0. So for trees, C3 is 0. For bipartite graphs, C3 is 0. For C4, I mean, it's possible to write down a formula. All I'm going to say is it depends. You're looking at closed walks of length 4. Now, to get a closed walk of length 4, you can go from vertex A to a neighbor B and back again, and then to B and back again, or you can go from A to B to C and then back along that path, or you can go from A to B to C to D and then back to A. So it's more complicated. You're going to get an expression involving the number of cycles and some other stuff. And so, and in fact, if you think about it, we've already seen the first example of a pair of co-spectral graphs is K14 and C4 with an isolated vertex. Now, K14 doesn't have any cycles, and C4 does have a cycle. It's in particular has a cycle length 4, so you can't determine the number of cycles of length 4 from the spectrum. The first example already shows that. I've got a comment here, which I suppose the worst. I could use an exercise, but I don't need to. For a characteristic polynomial, you can determine the length of the shortest odd cycle. You clearly cannot determine the length of the shortest even cycle because of the example I gave you just a second ago. Okay. And I don't think you can say very much about even cycles. So the point is that you do have some information, and this information can be useful, but you can't push it too far. Any questions? Okay. So I want to talk about constructions of co-spectral graphs. Now, and I'm going to go through 3. I'm not going to say much about this guy. So there's 3 families of constructions which give pairs of graphs that are co-spectral. So the first one is what I call local switching, or sometimes called something else. I've outlined 2 graphs here. The vertices should be numbered better, but that's the first numbering account which actually works what I want to do. So these two graphs, well, this is not meant to be an edge. So you've got a graph Z with 3 vertices, and you've got this graph with the 7 black vertices, and identifying 3 of the black vertices with 3 of the vertices in Z. So that's the construction. Okay. Now, the thing to notice is, well, 6 is adjacent to everything here, but nothing over here. 4 is adjacent to exactly one thing. I got that right? Yeah. One of these 3 vertices, and over here it's adjacent to the other 2. So the what I'm really saying is, if you sort of take the complement, well, let's do it with the matrices. So I've written down the adjacency matrix in a rough, well, part of the adjacency matrix in each case. And so I'm assuming the vertices are numbered in this crazy order, okay? And so I get a block of zeros corresponding to these 4 guys, okay? And then I'm worried about the edges joining those 4 guys to 1, 3, and 5. Okay, and so the adjacency matrix for the first graph is going to look like this. And so we have this guy. Did I give it a name? I think I was. Yeah, I'm going to call this B1. And we have this guy. And the thing to notice, as I believe about it before, is that this matrix is, in some sense, is just J minus this matrix. A few tries to get it right, which is why the numbering is a bit weird, but that's just compliments. And everything else is the same. Nothing's changed in Z itself. And the way it's set up, these are all the edges. So I've got 2 graphs with these 2 adjacency matrices. Now I'm going to show that these 2 graphs are cospectral, actually with cospectral complements. Now, as a reasonable question is, how do I know that the graphs I'm producing are not isomorphic? It's very easy to come up with a construction, and then you apply it to a particular example, and you discover the graphs are isomorphic. And so you're certainly right, they are cospectral. Now, this is from the data I've given you here, there's no way you can be 100% sure. So in fact, in some sense, the easy part of the problem is to come up with a construction for cospectral graphs, and the hard part is then to show that in general, these things, the graphs you're producing are not isomorphic. Now, I'm not going to fuss too much about that. Practical experience tells me that most of the time they're not isomorphic, and so it's not too hard to find examples that aren't isomorphic, and it's not a lot harder generally to find an infinite pair of examples not isomorphic. It might be hard to decide what proportion of examples are isomorphic, but the point is, it's in general not. If you come up with a construction, it's in general easy to produce an infinite. Of a pair of cospectral graphs, it's generally easy to tweak it and produce an infinite list of pairs of cospectral graphs that are not isomorphic. But that's based on experience with computation rather than anything else. So I choose not to worry about it. Also, of course, I can pick simple examples. I mean, if Z was just a cycle, then they would clearly not be isomorphic. Okay. So anyway, so I've got these 2 adjacency matrices, and I want to show that, and so I'm trying to prove these graphs are cospectral. And the way I came on this, in a certain sense, I decided, well, it's not that easy in general to prove 2 graphs are cospectral. You can try and compute the eigenvalues. That works for strongly regular graphs. Any 2 Latin square graphs of the same order are cospectral because they have the same eigenvalues. They have the same parameters, they have the same eigenvalues. Okay. But if the graph like this, there's no way I'm going to be right. I can see it, I'll be able to write down the eigenvalues. And at the time I was doing this, I was a graduate student, not that really matters. And it occurred to me, well, the easiest way to show the 2 graphs are cospectral is to show the adjacency matrices are similar. Okay, that's a lot easier than calculating. Could be easier than trying to calculate the character polynomial. So can I show they're similar? Well, the pattern we have is A1 has got this form 0, B1, B1 transpose C, and A2 has got this with B2 in place of B1. Now, the trick is I don't have to, so it seems like I ignore C. The idea is to assume Q is a 4x4 matrix, and it's orthogonal. Q squared is the identity. Now, a good question to think about is we know that two matrices with the same characteristic polynomial, two symmetric matrices with the same characteristic polynomial are similar. In fact, we know that they're similar via an orthogonal transformation. And you could ask yourself, how do I know it's orthogonal? But I don't care about that now. I'm going to construct an orthogonal matrix. I'm going to take this matrix. So Q is 4 by 4, and this is n minus 4 by n minus 4. And so I multiply it on, and so I'm constructing a similarity transform. And when I do that, the C doesn't get, nothing happens to C. Nothing happens to the 0. So the only thing that gets changed is that B1 goes to QB1. So the conclusion is that these two matrices are similar, provided this is true. Okay, there's too many Q's there. That's better. So if QB1 is equal to B2, then the two matrices are similar. Okay, fine. So how can we find such a Q? Well, it's very easy. You just take half the 4 by 4 matrix, or one's matrix minus the identity. Oops. So if you do that, the first thing is you get that Q squared is 1/4 J squared minus J plus I. Now J squared is 4 by 4. So J squared is 4 by J. So this is just J minus J plus I plus I. So Q is a symmetric matrix and it squares the identity. So Q inverse is equal to its Q, which is equal to transpose. So the Q is orthogonal. Okay, the other thing is if you check is that Q commutes, well, you don't have to check. Clearly Q commutes with the 4 by 4 or one's matrix because it's just a linear combination of that matrix and identity. And so that's telling us, that's consistent with the fact that the row and column sums of Q are all the same. Okay, and that's going to tell us that the graphs we construct are not just co-spectral, but they have co-spectral complements. But now, so okay, so now I've got Q, and so now I just have to check this. What if I apply Q to B1? What do I get? And you do the calculation, and you see it's mapping each of these columns to its complementary column. Now, there's more going on in this example, it appears, and there's a reason why I might have expected something like this, but the point is, this is the proof. This applied to that gives me that. Okay, so that's and so that tells me that this pair of graphs are co-spectral, no matter what you choose to say. Now you can extend this example. Brendan McKay and I wrote a paper on constructing co-spectral graphs before most of you guys are born, I expect, and we discussed this there. And so you can, this example, this can be generalized quite a bit. You don't actually have to have a zero matrix here. It just has to commute with the with Q, which is essentially commute with your one's matrix. So you could put a 4 cycle in there, everything would still work. Well, not sure about that, but you can. So you don't have to have a zero there, and some conditions you can join up things on the top here. And so, well, it gets even a bit more general than that. But so the point is that it's a very general construction. And it's quite interesting. If you look at the graphs up to about 10 or 11 vertices, most of the pairs of graphs are co-spectral because they're related by local switching. Okay, and if you look at the list of graphs, the proportion of graphs that are co-spectral up to 10, the proportion seems to be increasing. Now, the thing is that you can show by a probabilistic argument that the proportion of graphs which will admit local switching will go to 0 as number of vertices goes to infinity. Okay, and if you, Bauer and Spence actually went through and computed the co-spectral graphs on 11 vertices and 12 vertices, and they found that the proportions that were co-spectral were falling off. And so Harmer's conjectured that almost all graphs are determined by the spectrum of their adjacency matrix. Okay, but it's not true for small cases. And for small cases, what is driving it is the fact local switching. So local switching is in some sense the commonest source of co-spectrality. Okay, and it's easy to easy to describe, and the proof is quite simple. Okay. Now I think you can generalize a bit. I've described it here. Instead, take B to be a matrix of order 2k by L, and assume that each column consists of zeros or ones, or exactly half the symmetries of one and the other half is zero. Okay, and then take Q to be this, and then Q maps the 0 and vector, these vectors to their complements, and so you will get a pair of cospectral graphs. Now you can also take, as I said here, you can take 0 columns or columns of ones. Now, so in a sense, here I had a lot of columns of zeros, but I didn't need to mention them. I could change those to ones and everything would still work. Okay. Because Q applied to them would just map them to, so Q applied to the all ones vector, it just gives you the all ones vector. And so that won't cause you any problems. Okay. So the point is you have some vertices here and a set of vertices in Z, and each vertex here is adjacent to either all, none, or half the vertices of Z. And under that condition, you can do this complement, this local switching operation, and get a pair of cospectral graphs. Now, there's a related operation, which is less general, called switching or sidal switching, which is why we call it switching. I won't be going into that for no particular reason. But so my point is, this, a powerful method of constructing cospectral graphs, and it's easy to prove that it works. Now, for the next construction, we call this the partition tensor product, Brenda McKay and I. The thing we noticed, if you look at the small examples of cospectral pairs of graphs, we get this symmetry property. Now, this is the 4 cycle, and there's K14 with its isolated vertex. To make the symmetry, I've added one isolated vertex. And so each of these graphs contains 3 copies of the empty graph on 2 vertices, joined up in a symmetric fashion. Now, and so those graphs are cospectral, and if you throw away the isolated vertices, they're still cospectral. So the first example of cospectral graphs has this pattern. The second example also has that pattern. Okay, in this case, you've got 3 copies of the graph K2, and you've joined them up in this symmetric fashion. And they're cospectral. And this one's a little harder to see, but I've taken the 3 copies of this guy and done the same sort of joining. If you delete the common stuff, each of these has a component isomorphic to K2 and a component isomorphic to K1. You can throw those away. The 2 graphs left over are cospectral, and that's the smallest pair of cospectral forests. So the point is that this symmetry is quite common, and you can prove, in fact, a much more general result, which I'm not going to go into because the proof is more complicated. But so there is a common construction. Basically, you take a bipartite graph with white vertices and black vertices, and you replace the white vertices to copies of X, the black vertices to copies of Y, and join them up in this sort of fashion. And then it turns out if G and H are cospectral, you could swap the G's of H, and the new graphs are still cospectral. Or if the number of white vertices to the number of black vertices, it doesn't matter. So it's quite a flexible construction again, and gives you many examples. The one I want to talk about is more interesting for the consequences, and it involves some machinery that we will be using later on. So one way of constructing new graphs and old graphs is to take 2 graphs. Okay, now I'll stop there. Sorry, I've gone over time. Not being very good. Okay, that's not a bad place to break. Okay, so I'll start talking about this on Friday. Questions?